that appeared people were struggling with. A lot of these are all the same stuff here, and it's what are the significant figures and what's the implied precision. Okay, so there's no zeros. These are all whole numbers, so we count the number of significant digits is 1, 2, 3, 4, 5, 6. 6 significant figures. The implied precision. The error would be in the next position, so that's 0.00005. 0.0000 excuse me, 1, 2, 3, 4, 5 zeros, and then the next position over the original number, which is 3.32234, then times 100 to get the percent in precision. So on 0.000005 divided by 3.32234, and we get, this says E negative 6, so that's, oh, and then I got to take it times 100, and it says 1.50, and this says E negative 4, which means divide by 10 4 times. So divided by 10 once, 2, 3, 4. Once, 2, 3, 4. And I've already multiplied by 100, so it's 0.000015% error. Very, very, very tiny precision error. When somebody gives you this many digits, they're saying, I've really measured this really, really, really well. How many significant digits? Well, remember my little talk about the pushers. These 4 zeros are just pushing this 45 clear out there, away from the decimal. The decimal would be here, and this is pushing it over. So there's only really 2 numbers here that are measured. These are all just kind of pushers. So we got 2. And so the next place after the last significant digit is this one, and that's the one that would be half 5 in. So that would be 5000. So that's 5,000 divided by 450,000. And then we take it times 100 to get the percentage error. So 5,000 divided by 45,000, no, 450,000, 4 zeros, times 100, and we get 1.11% error, about 1% error. So this one is, since there's only 2 significant digits, there's about a percent chance of error, 1% error in it. This one, very little error, a tiny fraction of a percent of error. How about this one? Times 10 to the 4th. What's that mean? Well, if you multiply this by 10 4 times, once would make it 12. Second time would be 120, another 0, and another 0. 1, 2, 3, 4 places would be 1, 2, 0, 0, 0. But the number of significant digits, these are just pushers. And when you write scientific notation, you only list the significant digits, so there's 2 of them. And the percent error would be in this spot. So this is ones, tens, hundreds, 500 out of the 12,000. So there was 2 significant digits here, there's 2 here, so it should be near 1%, 1, 2, 3%, somewhere in there. What is 500 divided by 12,000 times 100 to make it percent, and we get 4.4%. ish. If you got two significant digits, you should have somewhere around 1, 2, 3, 4%. How many significant digits here? Well, these zeros are just pushing the number over this way instead of that way. That zero's not pushing, it's separating these. But these are just pushing them away from the decimal. The ones that push them away from the decimal are not considered significant. Now, if there was a number over here and then pushers, they would be, because they're between two numbers. These are not between. That one is significant. So there's 1, 2, 3 significant digits here. And the error would be in the next one. So 0, 0, 0, 0, 0, 0, 5. 0, 0, 0, 0, 0, 0, 5. That's the implied error over the original number, 0.000203. 3 significant digits, so it should be better than 4 or 1. It should be something like 0.1 or something. Let's see what that is. Only times 100. So 0.1234565, 6 zeros and a 5, divided by 0.000203 times 100 to make it percent, and we get 0.2%. Three significant digits, less error, better precision. 2 significant digits, more error. 1, 2, 3, 6 significant figures, very little error. How many significant digits here? 1, 2, 3, 4, 5, 6, 7. Should be less error than that. Let's see. So we got 7 significant figures. There's no zeros to be pushers, so we just got, in the last bit, 0, 0, 0, 0, 5 in that spot. 0.00005 divided by 154.1234 times 100. What's our percentage? 0.00005 divided by 154.1234 times 100. And that says divide by 10 5 times. So 3 divided by once, twice, 3, 4, 5. 0.00003% error. 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros. This looks like it's more. Something's wrong. I must have did this one incorrectly. Let's see here. 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. 5 divided by that. Let's do this one again. 0.00005 divided by 3.32234 times 100. Maybe I forgot to do times 100. So 1.5 e minus 4. So 1, 2, 3, 4. I got off by 1. There we go. So it should be 00015, 00003. 3 zeros, 1. This is 4. So this is smaller. This is got more significant digits, so it's more precise. How many significant digits here? It looks like a small number. It looks like it's pretty precise, but there's only one. These are just pushers, so there's one significant digit, which means there's going to be more errorness. 1, 2, 3, 4. That will be a 0 and half of the next one. So it's 1, 2, 3, 4, 5. This 5 zeros. 0.00000, and then the number, half of the next one, plus 5 more or less, divided by the original number, 0.00001 times 100 to get it to be a percent. And we have 0.000005 divided by 0.00001 times 100, and we get 50% error. If you only got one digit, you got a lot of percent error in your precision. Your height is 62.50 inches, 5'2.5". This is a small person. You pull out a measuring tape, and it says you're 62 5/8 plus or minus an eighth. So that's measuring tape says you are 5/8 of an inch, 5/8 in decimal. 5 divided by 8 is 0.625. So it's saying you're 62 and 0.625 plus or minus an eighth. 1/8 is 0.125 plus or minus 0.125. So if you add 0.125 on this, you get 62.75. If you subtract it, you get 62.50. So the measuring tape says you're somewhere between 62.5 and 62.75 inches. The laser says it's only off by this much. So your 62 point could be that much less before 5, plus that makes there, or over by that much up to 62.55. So the spread on this one is 0.125. On this one is 0.05. So they're saying the laser is more precise. And then, which one got you right? Well, this says that you're somewhere between 62.5 and 62.75. You are 62.5, so it got it right. It's okay. How about this one? It says you're between 62.45 and 62.55. Oop, got it right. They're both accurate. But the laser is giving you a more precise number. It's less error. If you do the percentage error, you'll find that 0.05 divided by this, 0.05 divided by the original number will be smaller than 1/8 divided by the original number. Okay. Now we have same kind of question here, but it's talking about your mass. That's really mass, but we'll call it weight. It says you weigh 52.55. That's what you really are. The scale says you're 52.5, plus or minus a half. So the scale is saying you're somewhere between half a kilogram less than 52, which is 52.5, which is 52, to half more, which is 53. So you could be somewhere within that 1-inch range. Now, a digital gym scale says you're going to be 51.48 plus or minus 1, so it's 51.47 for the low end, 1.01 less than this, 2.01 more than this, 51.49. So this one has less precision error than this one. If you took this divided by the original or this divided by this, you'll get the percentage precision error. And this one says better precision. ones. But which one is more accurate? Well, the real number is this, which is between these two and not between these two. This one missed. This one gets the correct answer, but gives you a lot of, well, it's around that, around 51 and a half, but it could be off by a ways. Well, how much it's off is precision. Does it have the correct answer in it? Yes. And so this one's accurate, and this one is not accurate. If you really weigh that much, it's saying it's down here. So even though it's giving you a pretty precise answer, it's not the correct answer. So not accurate. This one is accurate. That's what they want you to, that's what I want you to understand.